Okay, great. Kita nyo na, you guys can see the shared screen, right? Mag-thumbs up lang kayo or magsabi. Okay, very good. Thanks, Mads. Okay, so for today, we'll discuss instructions, but to give you an idea how the discussion will go, it's a bit, it's supposed to be a review of Triple E 105, or at least if you've uh, taken any class that has dealt with instructions before, it's pretty much it's cramped, or rather it's um, summarized in this discussion, because you see the important part really for this class is the instruction formatting, not really how to use instructions and things like that. Okay. Oh, I mean, yes, how to use instructions, but the proper way of coding in assembly is not gonna be discussed much in this class. We will pass through a bit on it, but we won't get into the details of it because, like I said, there's only a specific part that's very important here. Okay. So for those who don't know, because maybe some of you reached the time where CoE 112 was actually using MIPS instructions, or the MIPS architecture. For this class, and actually last year, the risk 5 was used for we were actually trying to target risk 5. Why? Because it's a free and open ISA. Actually, if you look at the um, documents online, our MIPS risk, the instruction architecture, the ISAs are actually free. The guidelines are there. But here in risk 5, it's an open source community where people develop it together. Okay, so it's not something like you have these proprietary rights involved. There are a few, but the idea for Risk 5 is that it's being developed by an open source community. Unlike the others like ARM, MIPS, and so on, uh, or x86 of Intel, they have sure they have the instructions, but the underlying layers or the discussions on how to build the computers, it's proprietary to them. So here, it's nice because anyone can jump in and help in the community. So if you actually go to this website down here, you can see more about the latest news about Risk 5. So if just like Mad's topic about machine learning, if you actually took Microlab as your class, you could have you had you would be designing machine learning processors integrated, or machine learning accelerators rather, integrated with Risk 5. So it's a very interesting topic too. Okay. Um, we are learning more about Risk 5 because we also want to develop our own community here in the Philippines to, so that students and faculty can participate. Okay. And it's the best ISA for universities because it's open source. Okay. So that's pretty much the motivation for Risk 5. That's why it's so cool. And there are nice things about it. Okay. So we'll get back to that. So why study instructions? Take note again, this is a review of Triple 105. And really, the reason why we need to understand the instruction set is these instructions are those they are literal instructions that commands the processor on what to do. Right? From the name itself, instruction, and I'm pretty sure that's the reason why it was named that way. Now we need to know how to build a machine that understands this instruction. Right? So if you remember from 105, the way we do data processing is using the von Neumann architecture. So you have an instruction memory that goes into the processor, and then it manipulates the data and it sends into the data memory. Actually, the instruction and data memory are shared into one, but for visualization purposes, we sort of separated it. But technically, they're all in just one big memory. Okay, and then they can process it at the same time. All right. So yeah, particularly when we do processor design, it's literally trying to, okay, if my instruction told me to add these registers or this value, how will my processor do it? Okay, it's literally just like that. Now, in some way, an ISA is like a plan. If you understand how the ISA works, the rules, the instructions, it's like giving your processor the specs that it needs. Okay? And by specs, I mean functionality specs, functions. Okay? Because, for example, between RISC and ARM ISAs, ARM actually has more flexibility, has more features compared to RISC, but it's more complicated to design in hardware. Right? So there are things like that they have to watch out for. But for our class, since we're working on RISC V, we'll just focus on RISC V instructions, right? Now, for every processor that you design, there's always these three design principles for an efficient hardware. And by efficient, we mean many things like low power or low energy, reusability, flexibility, and all several very nice qualitative things. However, there are three design principles that are mandatory, or maybe not mandatory, but three things that people always look for. Now, this is well studied by professors in the field of computer architecture, especially in Berkeley. Okay, and these three qualitative characteristics are, this is something that everyone is always looking for. Okay. Number one is simplicity favors regularity. Now, sometimes you would see designs that are very much complicated. Like, actually, if you try to look into x86, if you try to code things in assembly in x86, you'll be pulling your uh, brains out because it's not so friendly to the eyes. It's not so intuitive. You have to study it really, really down into the detail. However, complex things, because x86 is a complex, it's a ISA, it's a CISC processor, can actually do several things at once. Okay, so there's a trade-off. However, being simple like RISC-V, when you favor regularity, people would often use it more often. ARM instruction set is also simple. That's why it's the leading ISA for mobile devices, if I'm not mistaken. Okay. Because it's simple and again it favors regularity. Now, smaller is faster as well. So x86 is a big architecture. RISC-V MIPS is pretty much similar. ARM is much smaller. Okay? Because, for example, in RISC, you use 32-bit registers. 32 registers for its register file, while ARM actually uses 16 only. So, yes, smaller is faster because less logic. You only need less logic gates for that matter. And yes, I mean, smaller is better if you can pack it into a mobile device. And the third, which is something that you'll see next week when we discuss single cycle, is that good design demands good compromises. So what does that mean? If if there are features that you need to add in your design, because sometimes, let's say you have a processor, right? And then you want to add more features. Let's say a machine learning module inside of it. Now, adding a machine learning module inside that processor may be difficult if your processor isn't flexible enough, right? Your original processor. So, a good design means that, okay, we were able to make our processor to be one, simple, two, smaller, and at the same time, uh, we have the flexibility to modify only a few things. Okay, and that's something that we're going to discuss next week because you will see that, hey, say for example, I only have 5 instructions that I can support. If I add the sixth instruction, what can I change in the path, or rather in the data path, such that I can support the sixth instruction? Okay. And then if I have to change too many things, then that's a bad design. But if I have to change only, let's say, just add a single multiplexer, that's a good compromise. So it's a good design. Now, these are qualitative characteristics in designing a good computer. And just to go back with what I said earlier, it's important that the ISA is good because it's the ISA again. It's the one that gives you the functional specifications. Right. So keep in mind these things. And although I'm not expecting you guys to design something really good or so on, the reason why we're studying CoE 113 is so that I will show you and demonstrate. Okay, hey, RISC-V is a really good ISA because it satisfies all these three design principles. Okay. So let's begin. We can actually breeze through this, but okay. Typical types of instructions, we have arithmetic, so and or add, subtract, and or shift left, shift right. Memory instructions, if you remember the store word and load word, we'll get back to it in a bit. And conditional instructions, branching, and I would say jumping to in a indirect way. All right. So arithmetic instructions, literally the add. Oh, I didn't put it, but it's just all arithmetic operations. When you say arithmetic operations, it's add, subtract, multiply, divide, and or logical operations and all of those things. Now, the thing about arithmetic instructions, if you remember before, that we are actually using registers. And registers are short-term memory elements because we put data in them uh, just for a short time. You don't put the data and then it stays on forever. Usually change the data in the registers every now and then. That's why we call them the short-term memory elements. But they are memory elements to hold data for a certain amount of time. Now, arithmetic units use the data in registers or the data in the instruction, which are what we call constants or immediates. So say, for example, I'm going to add, let's say, I'm going to put it on register 3. I'm going to add 1. I'm going to add the data in register 1 and 2 and put it in register 3, right? I'm going to add it there. Whoop. So if the instruction is given that way, it will first pick up the data from x1. Whoops. I'm just going to write it x2, right? It's going to put it to an arithmetic unit, which we call as ALU. We'll get back to this next week. And then we're going to store it back into the register x3. It's that simple, right? So yeah, that's why arithmetic instructions are usually the first thing that people teach. Now, I mentioned earlier that RISC-V uses 32-bit, sorry, actually, yes, 32-bit, 32, 32-bit registers. Or let's just say first that RISC-V uses 32 registers, and then each register is 32 bits wide. Okay, and actually, the the real original RISC-V uses 64 bits, but we're using the 32 bits versions for this class, so that smaller is simple, right? And it's faster. Okay. Now in those 32 registers, we have this set over here. Actually, just this. Look at this, guys, over here. Ignore this for now because these are floating point registers. So we just focus on this first setup here. In the perspective of the hardware, they are just registers. And with the specialty that the register 0 will always be 0. As you can see, it's always hardwired 0. You cannot write on register 0. If you attempt to write on register 0, it will still be 0. So it's like fixed or hardwired to 0. But all the rest, all the 31 registers left from 1 up to 31 over here, or the 32th, 32nd rather, 32nd register, um, these are all in hardware, they're just registers. But in the software perspective, they actually have a name. Let's say, for example, X1 here is the return address. That's why it's named RA. X2 is usually written as the stack pointer. In terms of hardware, we can write on these things and we don't care what their names are. But in terms of software, they sort of give some sort of um, uh, there's an idea, or rather there's a purpose why they are named in such a way. For example, return address is something that they use for return functions, right? That, hey, if I call a function and have to return later on, the data is stored in this register x1, right? So I'm just going to mention it now, but just so you know how they do it in software. But in hardware, these are all the same registers except for x0, which is always hardware to 0. Now, functions are two types. We have the caller and the callee. The caller function is the one who calls another function. Let's say you'll see that later. Actually, yeah, we'll discuss this later to the far end anyway. Okay. So, yeah. So, important note is that we have 32 registers. Special register 0 is the special one. And all the rest, with respect to the hardware perspective, they're all just registers. Okay, but they do have a name when you look into the software perspective. All right, not so important right now, but just a good FYI. Now again, going back to arithmetic instructions, we have a list. There are actually dozens. Actually, yeah, there are several instructions that you can use. But for our class, well, we're gonna use this bunch here. Okay. Actually, there's a specific set of instructions that we're going to use, but this is just a list of examples that we can use here. Now, arithmetic instructions, we have two. We have register types, the R types, and then we also have the I types, the immediate types. So the R types are those who use registers alone. Like for example, add A, B, and C. These are registers only. I types or immediate types are those where the third argument, or sorry, the second source of data is actually a constant. So usually I types, they literally have an I at the end, right? So it's just literally doing, okay, add B and 100 together. That's an I type. That's an immediate type. If you don't have that uh, immediate or constant at the end, it's usually just an register instruction type. So for example, I get register B, I get register C, and then I put it in register A. So this is the operation that they do. So this is just a refresher. Hopefully, you guys can sort of remember what happens over here. And just so you know, from C code to assembly, we usually every time you type a C code, you convert it into its assembly version using a compiler. We call it the compiler. Okay? Because from assembly code, it becomes into a machine language, which we're gonna discuss later. So it's a machine language later, but the one that converts that is the assembler. Okay? I'll just mention it now, but we'll get back to it later. So say for example, I have this C code where I add J and H together. I'll subtract it to the sum of I and J, okay? And then store it in F. So if I'm gonna write it in RISC-V assembly, let's assume G, this X20 is G, 21 is H, 22 is I, and then 23 is J. This first parenthesis out here, so that's the first parenthesis, G plus H, will be stored in X5, and the second parenthesis, I plus J, will be stored in X6. Right, so you could follow what's happening up here. It's very easy to translate because it's sort of a very, it's very direct. Right, so for example, I'm gonna add J and H together. I'm gonna store it in register 5. I'm going to add I and J together. I'm going to start in register 6. And finally, if I want to subtract these two, I just call the sub instruction. This is F. 19 will be F. And then X5 was the original G plus H. And X6 was the original I plus J. It's very simple, right? So I'm just going to do it that way. And then I can do this operation already. Right? Now, observe that the destination register comes first. Okay, the destination register comes first. The format for most of it is that, okay, destination always goes first. Then don't get confused, but it's important to know the order. The two sources, the first one is always source 1, and the second is always source 2. Take note of that because we need to identify the positions later on. Because we're going to put it in its machine counterpart. Okay. So again, for every arithmetic instruction, you have the destination, you have source 1 and source 2. That's it. Okay. So the next type of instructions are called memory instructions. So if you remember, we have the load word and the store word instructions. So the load word is literally getting data from the memory and load it into an a register. So in this example, load word A 100B, what you do is that, okay, I'm gonna go get and grab the contents that is stored in the memory. So A here is like the memory at the address B plus 100. So B can be any starting the base value. Then you're gonna have to offset it by 100. So let's say the base value is originally at 0, and then you add the 100 over there. So I'm gonna grab from the memory. Okay, it could be from array, or actually it's just literally from the memory. And then I'm gonna store it in register A. Store word is the opposite direction. So whatever is in the contents of register A, I'm gonna store it in the memory address B plus the offset. Okay, so the base address plus the offset. All right. So to make it easier to remember, 100. If you see these things, it's usually just okay. Grab the value in register B. Right. So yeah, I forgot to mention, but B here is a register. Grab the value in register B and add the offset. The same thing for store word. Grab the value in register B and add the offset. That's the target memory address that we're gonna get or store the register in the data in register A. Right? Very simple, right? Very simple. So say for example, I have this C code that says, okay, I have some data in register H or some data in variable H, but I want to grab the data at this location. Okay, I have an array A that's it has some data in it. Okay, let's say that I want to grab the eighth byte, actually the ninth byte rather, because we're always indexed at 0. So I'm going to grab the ninth byte. So A8 over here. Let's say if it's a byte, let's say it's, I don't know, let's call it FF. Okay. And then I want to store that at address, I want to add it to H, and then I'm going to store it at address 12. So the 13th byte. So it's the ninth byte. And then I want to store it later on the 13th byte. Take note that the very first here is the 0th byte, okay, because we're index 0. So it's simple, right? So assuming that, okay, so how are we going to do this? A8 here, grabbing the value at address 8 is this one, right? Now you might wonder, okay, how come we are using an offset of 32, not an offset of 8? That's because you need to multiply the offset by 4 so that they are word aligned. We'll get back to that in a bit, right? So I have an 8 here. That the real address that we're going to access is, okay, let's first get the base of A, which is stored in x22. And then I'm going to add the offset of 8, which is 8 times 4. Okay. So I'm going to add these two together. I'm going to grab that data and load it on X9. So X9 actually stores A8. Now here, if I'm going to add both, what I'm going to do is that, okay, X21 here contains H. This is A8. And then I can overwrite. Nothing stops us from overwriting X9 to contain H plus A8. Right? And then I'm going to store that H plus A8 because that's the current value of X9 over here. Right? And I'm going to store it at address A12, which is 48 because that's 4 times 12. Okay? Plus X22 because X22 is pointing to the base address of A. Right? So it's going to store it somewhere here. Okay? So it's very simple, right? It takes time, but review this recorded video again to just to keep track of, okay, how did we actually do that thing, right? Okay, so a little bit more on memories. Why do we need that times 4 component, right? Like here, why I wanted to get the one indexed at 8, but how come we needed to multiply it by 4? Okay. So memories are byte addressable. So what does that mean? Technically, if you open up or if you go into the memory, the actual hardware of memory, it's ordered this in this way. So for example, the first byte 0 is at address 0, right? Because address 0 is pointing to byte 0, right? Address 1 is pointing to byte 1, address 2 is pointing to byte 2, right? Because it's byte addressable, meaning, and usually people get confused with this. When we say it's byte addressable, every increment in the address is pointing to 1 byte only. It is only pointing to 1 byte. So it's here, right? So we're happy with that. Yay. However, here's the catch. Memory is, yeah, this is a 1D array, but we usually reorganize it in such a way that they are word addressable. Or sorry, not word addressable, but they're organized to contain words. Right. So technically, again, memories are byte addressable. They are just 1D array, but we organize the visualization of those bytes into a set of words. Because, as mentioned earlier, right, the 32-bit registers of your RISC-V contains 30. Sorry, the 32 registers of your RISC-V contains 32 bits each. So that's how many bytes? That's 4 bytes wide, right? That's like literally one word is actually 4 bytes. So this note over here. So you have to reorganize them such that byte 0 is still here, byte 1, 2, 3. Okay. So these two are the same. They're just reorganized in a different way. So if I access byte 0, right? If I say address 0, I'm accessing starting from byte 0. But then because we're transferring in terms of 4 bytes or one word, that's 32 bits. We're transferring or using data in terms of words. You have to increment the address by 4. Otherwise, you'll be misaligned. Okay, so that's what we call by word alignment, right? So say, for example, my first data in the data memory or instruction memory is pointing at address 0. But that data is not just getting byte 0, it's getting bytes 0 up to 3. So that's 4 bytes. See? 2, 3, and 4. That's 4 bytes long. Now, if I need to get the next word, the next set of data in my data memory, I don't access byte 2. I have to specify, hey, let's start at byte 4 because you already took the first 4. So the base of the next word is at byte 4, right? And then you grab the entire word again. Okay, so that's what we mean by word aligned. So our memories again are byte addressable, meaning every increment in the address pertains to 1 byte. But we are getting data in terms of words, so we need to align them with words. So that's why you have to skip count by 4, 8, 12. So in our example earlier, if it is indexed at 8 and I want to get the data at index 8, technically I need to get the data at address 8 times 4, which is 32. So the base address x22, wherever this A is starting, plus 32. Because I need to get the 30-second offset relative to x22 to get the entire word. Right. Now sometimes people there are options that take only the byte or half the byte, but we won't be doing that for simplicity. I think it's more important for me that you just understand, okay, how do you build basic computers that are word aligned for now. Okay. Now note some RISC architectures use double words. Actually, the 64 version use double words, meaning that's literally 64 bits. That's double words. Okay. We'll only use words for our class, right? For simplicity. Again, smaller is better. All right. Do you have any questions before I move on? None? Okay. The nice thing about recorded sessions is that you can always go back to them later. Okay. The last set of instructions are conditional instructions. So we have the branch if you're equal to or not equal to. So if RS1 is equal to RS2, go to a certain uh, instruction number. Okay. So the way you do it conditional instruction is that, okay, you compare the value of RS1 and RS2. If they are equal, you jump, you have to change, or rather, you have to jump to the instruction at number L. So L here is a label, but usually there's a specific immediate value there. Okay, there's a specific constant rather that tells you, hey, I have to jump to this number, to this instruction. This allows us to move from instruction to instruction. Because earlier, these operations like memory instructions, they only modify the what do you call this? They only modify the data memory. But here in conditional instructions, you don't modify the instruction memory, but you can move from instruction to instruction using conditional instructions. Okay. So you also have set if less than and branch if not equal to. Okay. So it's very simple. Let's say, for example, if we have this C code, actually, I forgot to mention, but conditional instructions actually are used for all conditional statements in C or Python. So say, for example, if I is equal to J, we add, otherwise we subtract it. It's very easy to do, right? So let's say we do the RISC-V assembly or the compiled version is that if I x22 is I and x23 is J, and we compare them, if they are not equal, we jump to the else condition. But take note, the else here could be some other uh, or naming, or actually the else here is an exact number in the instruction memory, right? So if, for example, this is instruction 0, 1, 2, 3, and then 4. So this else here could be 3. Okay. So if I and J are not equal, we jump to the else part. Okay, I think it is wrong. Branch if not equal to. Okay. But if they are equal, okay, so it doesn't necessarily translate to this one, right? Actually, no. Let's make this as not equal. Oh no no no, that's right, that's right. I'm the one who got confused. Pointer options spent. So for example, if I and J are not equal, right? Then we jump to the else part, wherein they're gonna have to subtract it, right? They're gonna have to do the subtraction. So it makes sense, right? If I and j are not equal, we do the subtraction, right? If I and j are equal, okay, if I and j are equal, then we do the addition operation, right? And so it's consistent with the code above, right? So again, if I and j are not equal, we jump to instruction number 3, which is to do the subtraction. Otherwise, we don't do this instruction. We just make the compare and then we just proceed as is. If I and j are equal, we do the addition, which is you do the addition over here. Now here's the interesting part. If you want to jump to another part, okay, if you look at this, if x0 is equal to x0, you jump to exit, which is pointing to instruction 4 or to whatever is in here. Okay. Now it makes sense because if zero a dollar x0, remember that's the zero register, is always equal to the zero register. And if it's true, then you jump to the exit. Voila, right? So you see the point of conditional instruction is that okay, you can move around your instruction memory. Okay. So that's the conditional instruction. So here's a more sophisticated example. Let's say while we're in this loop, while save I, so it's like we're scanning through some save register, or rather some save value in the memory. We're trying to scan all the save. We're trying to scan throughout the entire save memory, and if save I is always equal to k, we keep scanning and scanning. But if there's a difference between save I and k, we get out of the loop, right? So it's simple, right? So this is this is shift left logical x10, x22, and 2, meaning this x10 here is actually the uh, what do you call this? The I that you're using, okay? And then x22 here is the I plus 1. All right. So sorry, this is I plus 1. What we're doing is that, okay, we get the I plus 1 variable, shift it left to 2. The reason why you're shifting it left to the 2 is because that's doing the I plus 1 times 4, right? So we're doing the offset over here. And then what you're going to do, you're going to store it in 10. And then in 10, x25 here is the base address for save, right? You add them together, you put it here in x10, and then you load the data in x9. So x9 here is the save, the updated value of I, right? The new I over here. And what you're going to do next is that x34 here is k. So you're going to compare. If save I and x24 are not equal, you go out of the loop immediately, right? So that's what it's trying to say. And then otherwise, if they're not equal, okay, let's update my I plus 1. Right, so that's x22 here is the current I. Actually, yeah, let's put it as the current I. Let's put this as the current I. That's the current I. Right, so it's I here is the current I. You add plus 1 to the current I. So this operation, add I here is the I plus 1, actually. And then you're going to branch again to loop. You're going to go back to loop. And then you're going to go it over and over and over again. So technically, this C code, or actually not technically, but this C code, if you compile it into assembly, it will become like this. Okay, dokie. So I guess it's a very quick review because I want you guys to recall that, hey, this is how we actually do C code instructions again. Yes, you might need it, although it's not perfect, but when you do your ME2 and 3, you're just going to have to understand, okay, how does the loop flow? All right. Now we have this thing called pseudo instructions. I'm just going to mention it here, but there exist pseudo instructions which are not really part of the RISC-V ISA, but they exist as translators. They're not part of the base RISC-V ISA. Say, for example, NOP instructions are no operations, meaning if you run it, it's supposed to do nothing at all. When you put NOP in the assembly language, it's gonna do is that it's gonna, instead of doing a NOP, like a dedicated NOP instruction, it's gonna do add I x0 x00 because it's like doing nothing at all. You're adding 0 to the register 0. That's literally doing nothing. So that's a NOP instruction. Load immediate, well, there's a myriad of sequences. Move, for example, you're going to move the data from the source register to the destination register. So it's basically, okay, adding the source to 0 and then just adding it to RD. So it's literally copying it from the source to the destination register. And there are several pseudo instructions. The reason why pseudo instructions exist is that you don't have to make a dedicated instruction, let's say the NOP instruction, right? You could argue that, hey, why don't we put it as all zero, an instruction that has all zeros, right? I mean, yeah, but if you can actually reuse some base instructions, that also does nothing. So why don't we just use the base instruction instead? We might have other special cases for this 00000 instructions. That's why pseudo instructions exist. Okay? So we won't be doing this actually, but it's just nice to mention. So here's the important part. So much for instructions, so much for the review. Um, I suggest you guys also try it for yourselves. I think the homework has a very nice um, example just to help you guys recall how we do instructions before. But we have different format types of instructions. So each instruction has a certain instruction format. By format types, if you're given an instruction type, it has its own machine code, right? And that's the important part because it's the machine code that the processor tries to understand. So we have R type used for register to register only. I type, those are those with constants, and S type for storing type operations. We actually have two more, the B type, the branch, and the J type for the jump. But we'll discuss those next week instead. So actually, no, we added the B type here. Cool. Anyway, so R type, I type, S type, B type. So again, every instruction that you get in the in the instruction memory is 32 bits wide, right? And those 32 bits have, they are unordered, they are in order. Okay, so this part here is the 32nd bit, right? And then down here is the first bit. So the MSB and then the LSB, right? Well, technically, this is bit number 31 because we're index 0. And down here at the bottom is bit 0, right? So whether you're R type, I type, S type, and B type, they have this certain formats. So these are the format types. Okay. And then what a nice thing about it is that, see, the very nice thing about RISC instructions is that they're very ordered. Let's say, for example, RS1, they're all consistent for all R type, I type, S type, and B type. So when you start to make your decoders that try to understand, hey, what kind of instruction you are, you don't have to change much. There are several of it where you can use it at the same time. RS1 and Func3 for that example, and of course the opcode. For destination types, R type and I type are pretty much the same. Okay. Also the for store type, you have the source 2 for R type and S type. And then for immediates, it's sort of the same, almost the same, but the only downside for RISC instructions is that, okay, the immediates part is a bit hairy. It's a bit messy. All right. So you need to read the instruction ISA manual for more information. But the moment you open that manual, actually, we have a cheat sheet in Uble. It's the RISC-V card. You can also see this kind of formatting. Okay. So use the reference RISC-V as spec sheet for guidance when you get lost. So here's a more detailed example. Let's say, for example, add and sub instructions are R-type. And then you can immediately tell, okay, which is add, which is a subtract, by looking into the func7 form field only. And by func7 field, it's this one, right? So you can see it there. And they only differ by this the 1, 2, 3, 4, 5, 6, sixth bit or bit 5 of the func, right? And you could see there, some of them are pretty much the same. For R-type, the add and sub have the same func3. For opcode, it's also the same. So for R-types, the opcode is in this format, 00110011, right? It's very simple. So, actually, 1, 2, 3, 4, 5. We have to take this out. And you have to take this out. Sorry, I added too much zeros, but it's only this much. Okay? For immediate types, they have the same formats, no problem. The func trees are different to differentiate from add I from load word. And take note, the load word instructions are immediate types. They have different opcodes too for security that, hey, I'm actually doing a load word, and so on and so forth. Store word types have a different format because it's using the S type instruction format, right? So only store words instructions are store types. Actually, it's a dedicated one. For func and opcodes, you need to check the RISC-V spec sheet. Okay, so go to page 104 of the RISC-V spec sheet over there. Or in our RISC-V cheat sheet, there's also a guide too, so you could look at that. But if you need more details, go to the RISC-V spec sheet. Time check, okay. So a few more examples, just to make sure that you understand. And it's really important because these are the things that you have to decode in your project. So if I want to do add x9, x20, x21, what are the things that you have to identify? And this is a good exercise because it's also part of your homework, and you will see it in your next homework next week too, right? So we know it's an R type instruction. So immediately bring out, okay, this is how we're gonna fill this up, right? This is the format. This is the instruction format. And then what you're going to do is write down the decimal form. You know func7 is 0 based on the spec sheet. RS2, this remember, this is RS1, this is RS2, and this is RD. RS2 is 21, write down it's 21. RS1 is 20, write down it's 20. The destination, oh, so the func3 is 0 based on the spec sheet. The destination is 9, write down 9. And then the opcode, look at the spec sheet, it's 51 in decimal. But you can transform into binary form. So 0 is 0, 21 from decimal to binary is 10101. 20, 10100. The func, the destination is 01001. And then the opcode, just copy it from the spec sheet. And then you concatenate all of this together. You get this long line of machine code that's equivalent to this in hex. It's simple, right? It's that simple. So if you do the add immediate, it's the same thing. So this is sort of the routine that you're going to do. You know the instruction type, grab the formatting, get the decimal form, fill in the details. So the immediate is 100 in decimal, right? It's not in hex. It can be in hex if you put the 0x something here, but let's stick to decimal for now because it's easier to read, at least for practical purposes, right? And then, so the image is 100, the RS1 is 20, func, base it on the spec sheet, destination 9, opcode is 51, and then fill in all the details, and then write the hex code. That's it, right? Load word, same thing. What's the load word is 240. Again, it's in decimal. And then you're just gonna grab this is the destination RD, this is RS1, right? So RS1 is 10, destination is 9, not a problem. Func3 gets the spec sheet, opcode spec sheet, immediate. What is 240? So you have to convert that manually in, it's in decimal, but you convert it either in hex or in binary form. Okay, and then you just fill it up. And then you're gonna concatenate again all of these until you get the hex. Same with store word. Since this is recorded, I'd like you guys to try it on your own. I won't go to it all throughout, but these are a few examples that you can look into. Oh, sorry. By the way, for the store word, take note it's a bit trickier, right? Because the immediate field in the store word is not in order, like here in immediate field for I type instructions. You take note and be very, very careful because the immediate field in the store word is very specific, right? So you store, let's say, for example, 360 in hex is 168. So if I'm going to write it down, that's 0001, 6 is 0110, and then 8 is 1000. All right. So bits 11 to 5, that's the 12th bit. This is 11, 10, 9, 8, 7, 6, and 5, right? So bits 11 to 5 are stored in the first 7 bits of the S type, right? So whatever this value is in decimal, that's 11. Or just copy the entire bits here over here. And then the lower bits from the lower 5 bits from 4, 3, 2, 1, and 0 are stored here in the next 5 bits in the lower part of the instruction. So you have to copy that thing. So cut that there, copy this thing, put it there, right? So it's not like the ordinary load word immediate that it's ordered. you have to be careful about slicing or reorganizing those bits. Okay, so that's something that you have to watch out for. I don't know why, but that's how they made store words. Okay, we have to follow the ISA specs because it is the spec. So branching is the same thing, but again, I'd like you guys to sort of be wary of this branching part. And take note, the branching type uses 13 bits. Well, it's 12 bits, but the immediate version of it should be 13 bits long. Okay, so take note of these bits. Let's say, for example, this is bit 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh no. 1. Oh, because I used 13. Sorry, sorry. Let's do it again. So that it's very, very, very clear to you guys. Because I think it might be a case for confusion. So 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. Okay, so I'm going to take this out first. So again, if you look into the spec sheet, it says here bit 12 is in the very uh, bit position 12 is the very MSP, right? And then bit position 11 is in the lower end. So this guy goes over here. And then bits 10 to 5. So you grab this to put it over here. And then the last bits are put over here. So there's this slicing thing that you have to watch out for. Okay? Actually, I would like to say that's the end of the discussion, really, because this is the most important part, the instruction formatting, right? That you have the homework will be there to help you, okay? And it's a good exercise for you guys because the moment you start making your processors, you're gonna have to think about, okay, how am I gonna slice these things? Okay, that's the very important part. Now, just to mention this last part, which we call procedures, but I'll just go through it very, very quickly because um, it's not really that important for now. It's meant for software engineers because there's a proper way of actually using instructions and the registers that you have to use. Okay. So procedures are also known as functions in assembly language. It's nothing more than just functions. Okay. It's the same thing. And the nice thing about procedures and functions is that it's easier to structure programs for reuse, right? Let's say, for example, I want to pay grocery, but when I pay my grocery, I have to count the number of items that I have. Right. So this function, pay grocery, has a sub function called the count grocery items, which is another procedure or a function. And the purpose of this count grocery items is just to count the number of items that I have. And I'm just gonna sum them up or do whatever I need for them later on. So pay grocery here is what you call the caller. Why is it the caller? Because it calls count grocery. Okay. And count grocery here is the callee because it's being called by pay grocery. So that's the difference. It's a nice term that you have to watch out for because some people use it, the caller and the callee, right? So if you make that into the assembly, you compile it into assembly, you have the procedure named pay grocery, okay, that does something, and then that pay grocery actually calls the procedure or jumps to a different instruction count procedure to check the number of grocery. Or no, sorry, that should be count grocery, which is this one, right? And it does everything that it needs to be. And then eventually, it will have to jump back to the original one, to the caller pay grocery. So that's sort of the idea over here. So how you build it in the C code is pretty much similar how you build it in the what they call this in the assembly language. However, there are certain rules that software engineers sort of need to follow. Right. So here's the thing. When you make procedures, okay, you have these steps. The software engineers need to follow these steps. First, they need to save the parameters in place where the procedure can access them. Because you are limited to only 32-bit registers, what if you have a function that has more than 32 values, right? Then there is you can fit everything in 32 bits only. You have to find a way, okay, how do we or organize it in a very convenient way, such that all the variables or parameters that I use in my functions doesn't mess up the entire program, right? Because I'm only limited to 32-bit 32 bit registers, right? So there's a proper way. So you save them into some specific places. You can put it in memory, you can put it in specific registers, right? Then you transfer the control to the next procedure, to the CoE procedure. You acquire storage and resources for that procedure, and then you perform the desired task. Yeah, you're gonna see this pattern later on. And then what you're gonna do next is they're gonna put the result into specific registers or memory. You're gonna return the control to the master procedure, and then continue with the original point where continue at the original point where you call the CoE procedure. Right. Now I know this sounds so fast and hairy, but I'm doing it because it's recorded anyway. But you're going to see in the next example. Right. So yeah, so the problem really is that what we have too many variables. Take note again in the software perspective, there are save variables. Like for example, x8 and S2 to S11, these are save of registers. You save some parameters or variables in these registers. You also have temporary registers, which software engineers use for literally from the name itself, temporary. You can put data there, you can take it out, but it's not meant to save things. It's like software engineers understand that, okay, if I put it in this certain registers, like T3 to T6, that's register numbers 28 to 31. They have an idea that, okay, this will be temporary for the callee registers only or the caller, depending on who needs who. Um, and then what they're gonna do is that okay, it's temporary. I know the data here will change very much often, unlike save registers where the data changes a little bit less often. So these are specialized registers. That's how they call it. Now, what if it doesn't fit all? Right? All of these don't fit. You have to put them into the memory stack. Now we're not going to discuss it anymore in 113, but in the data memory, okay, actually in the entire memory, you have a bunch of allocation for instructions. You have a bunch of allocation for the data that you're going to use. And then you have a bunch of allocation that's meant for the stack. Now, the stack is meant for what if I really have more than 32 variables that I have to play around with. Okay. So just an FYI, but we won't do it, discuss it much right now. So the very, very simple example is a swap, a bubble sort code. And one of the things in bubble sorting algorithms is that you have this swap variable. So if you look at here, what it literally does is just it swaps position uh, between two locations within a memory or in an array. Okay, is that simple? So this swap here is a callee because later on it will be called by a bigger function, which is the caller. Okay. Now, if I put it in a RISC-V assembly language, the swap procedure, you can see here this labels or no, it's just a swap procedure. It does this entire thing. But then I guess one thing that I'd like to point out here is that it pro this X6 and X11 or these registers are most likely temporary registers. So let's see. X6 to X11, yeah, you can see here, right? X's are temporary registers. X11 is an argument register. So it's like saying, you can see here that the code swap uses int v as an argument or k. So that k there, okay, is an argument register, right? That's probably most likely X11. X6 here is just a temporary register. So the way people, software engineers do it is that, or the compilers do it, who make, or software engineers who make the compilers, they are wary about, okay, what's this X6 and X11 for? In the hardware perspective, we don't care. We just know that, okay, it's just a register. But for software engineers, they know that, hey, I'm using it for this specific purpose. And then they have these things that they do with swapping of things over here. Okay, not a problem. And then you have this jump and return. So jump and link register is a literal, remember, X1 is the return address. You can see here. Because swap is being called by a bigger function, you return to that bigger function. That's what JAL return does. Okay. So if I'm going to do this bubble sort, this nice looking for loop here, we won't get into details of it. But just so you know that it's like we're iterating between I and j variables. Okay. Now observe that if I do it for the entire array, okay, I'm actually calling the swap function. So sort here is the caller function, swap is the callee function. Okay. And So it's gonna run. This sort has its own set of instructions, and then the swap here is this set of instructions over here, right? So that's what's gonna happen. So if I'm gonna do it into assembly code, it's way much longer, but don't worry about it. What you want to One thing that I'd like you guys to look at is because these things, okay, sure, we are passing things here and there, and then if you try to do this for loop over here, there may be too many variables, right? And of course, in the software perspective, I don't want to use my save or argument registers too much. I can probably use my temporary registers, but for safety purposes, why don't I put these variables into all these parameters into the stack? That's why every time the compiler tries to make this code, you'll always see this setup here, wherein it moves a stack of pointers and it saves certain values, right? It could be the I, it could be the J, it could be the K, right? It could be the V. Because if you notice here, V is being passed on to what? It's also being passed on to the swap. So it's like, oh, I'm going to need the V again. So why don't we put it in some stack pointer over here? A stack, sorry, not stack pointer, but let's put it into memory. That's why it's using store word. So if you remember your memory, you have the instruction, the data, and then you have this bunch for the stack only. Why don't we put some of the parameters in the stack? Okay, so that I have more space in my registers. And then what you're gonna do is that you have this set of instructions here that, okay, I'm going to proceed with this for loop over here. So this here, I'm not gonna explain it in detail, but you can review it later on. It's well commented anyway. But all it does is just handling this set of for loops, right? And somewhere down the line, you will see that we're calling the swap. Jump and link means, okay, I'm gonna go to swap operation, which is this one. Oops, which is this one, right? The swap procedure. But I'm going to store my current address in X1. Again, the return address. That's what the JAL instruction does. And then, if I'm going to continue further, if I jump to the swap procedure, let's say, I'm not sure where it is over here. So, yeah, I'm going to go do the swap procedure, which was called earlier, right? I didn't put it over here. But if I'm going to do that, later on. And let's say I was able to complete my swapping correctly. The moment we go to the return function, because the swap already returns immediately, right? When it does the swap operation, it returns and it's going to do the for loop again and again until it completes. But the moment you are done, the moment you are complete, right? If we're going to return to the outer loop, there's a part there that says, hey, we can exit. You can see this exit instructions, right? If I exit one, the main exit, you'll see here that, okay, I am returning all the values from or rather, not returning all the values, but the for loop one, all right? This is for loop one. Okay. Everything that I've saved in the stack originally up here, when I am done with the sort function, what do? I return all the values to the registers. Because this sort function might be used somewhere in a bigger function again. Maybe in the int main void. So first thing again, I guess the entire point of a procedural example is that if I call a function like sort, I need to first save parameters in the stack. I proceed with my function, right? And then when I am done, when I need to return, I return these values over here. Okay. I have to return it again so that I can continue wherever this sort function was called. All right. Yeah, that's pretty much it. So it's a good FYI, although it's not so important, because it sort of gives you the idea. Hey, what's the importance of really doing this computer architecture, right? And then it gives you insight. Okay, so this is what my software engineers need, and you guys as digital designers or hardware designers. Okay, it gives you insight on, okay, so I need to work on this thing so that it's easier for them to do, right? So it's a good FYI because it gives insights to what you need. And observe that the von Neumann architecture is a bit memory hungry procedure because over here it's always moving memory and then memory again, right? So it's a little bit somewhere that lines. So yeah, that's pretty much it actually. So in summary, instructions give insights on how we develop the RISC-V processor. The, there are several types and considerations, but most of them are similar. That's why it's making it easier to design a processor. That's why when you go to the RISC-V spec sheet, everyone who has helped out in the development of the ISA all of this in mind. Okay, how do you make it easy to develop your own architecture? Now, the important parts that you have to take here really is one, the use of the 32 registers. In our class, each register is 32 bits wide, so you have to know that. And this other part is really the instruction formats. I would also add actually the how the instructions work. How the instructions work. Instructions. You know, I mean, it's good that you know how they work because they also give insights later on. Okay, how am I gonna develop my ALUs, my registers, and all those things? Okay, how do you do the branching? How do you do the jumping? So that's something that we will do next week because next week we'll dedicate the entire week to developing your single cycle processor, and it's also the start for your ME2 and 3. So ME2 and 3, I'll give you 1 month to work on it. Okay, because it's literally the single cycle process that you need to make. And to be honest, it's really easy to do. You can do it in what, a day or two, because it's very simple. And yeah, the moment you're done with that, more or less you have a good foundation on how to make processors. Okay. So digital design or being an artist designer is fun, and you're gonna. I hope you guys will be able to do that the right way. Okay. References, please use this book, previous 113 lectures, and the Harris book that we have. Actually, I do recommend this way, way much better. I should put this picture here next week because the Harris book is, it has a very good step-by-step approach to make the RTL design. And I do recommend that you read that because the moment you do, you can make the single cycle processor by just following what is written there. Right? Of course, you need to do a little bit adjustments, but I guarantee that you can make it easily. Okay. Any questions? Time check. A little bit, like an hour and a half, 2 minutes. No questions. Uh, okay, good. So I will see you guys next week, and thank you for coming. I'm happy that you're attending. Makes it focus time.